Come on in, everyone. Feel free to ask me any questions while we're waiting for class to start. Still got a minute left. If any of you have any questions, again, feel free to ask them before class is started. We're going to start in the next minute or so. We've got 12 people now in the meeting. That's a pretty good fraction of the class. So, there's another one. I'm going to check something out right quick on our syllabus to see what I got scheduled for the test date and all that good stuff. This is the right one. Okay. Okay, let's Okay, I think I got it all figured out. That's good enough. So we're gonna go ahead and get started. Does anyone have any questions? I know I've asked several times for the people that are already here, but just want to make sure anybody has any questions before we move on. Oh, two more came in. Three more came in. All right, so I'm gonna go with uh, starting up class. Another person just came in. Uh, like I said, you can always ask me questions about homeworks and any other stuff at the beginning of class. Even if I forget to do it, just stop me. Y- what I'm looking at, I just looked at our schedule according to my syllabus. I think I have it all set up right. Yeah, so if you notice in our syllabus, it has that on Monday, January 29th, we have the motion detector lab, uh, which means we're not doing a test that day, but test 01 online is due Sunday. So I did last night make sure everything was posted, and you'll see that the actual equations you need, as well as the periodic table, as well as the cover material from the textbook, are all in not only your quiz, but in your practice or in your practice test, as well as your test. But that online test is due Monday, or excuse me, 11:59 p.m. Sunday, and then the following week, we have a lab. But that lab is strictly for face-to-face midterm, and I call it midterm because, but even though there's like three of them, but that basically that's the first of the face-to-face tests. So, any questions on that? All right, the practice tests are already up, as well as the test is up, and the due dates are all listed in that, so you shouldn't have any problems finding it. That being said, I want to go ahead and begin class. We had actually started or finished chapter two, but there's some aspects of chapter two that I wanted you to understand for sure. I did focus a lot more on stuff that you're textbook tried to do a little bit, but didn't waste a whole lot of words on it. You can sort of piece it together to see it, but in reality, what I expressed to you guys is that the acceleration due to gravity behaves the same way on an object moving with a velocity that's big or small, to the left, to the right, in or out, as well as up or down. So literally, even if you throw in the direction of gravity, the velocity will still only change by 9.80 meters per second each second. So that literally means if it left my hand at 0 seconds with 10 meters per second velocity downward, then after 1 second it'll be 19.8 downward, and after 2 seconds it'll be 29.6 downward, and so on and so forth. Uh, Not only that, that also means the actual distance traveled as a result of acceleration acts completely independently of the initial velocity. And you can see that in the kinematic equation where I wrote x is equal to 1/2 at squared. That's the distance part that's purely due to the acceleration, plus v0t. That's the distance part that's due to the initial velocity and the total time that it was traveling. Because remember, if it has an initial velocity of 3 meters per second, every second it's going to act like, hey, this is a constant velocity, so I'm going to move an additional 3 meters. I'm going to move an additional 3 meters. I'm going to move this additional 3 meters. But in reality, if those two are fighting each other, if the distance traveled by initial velocity is in the opposite direction that gravity is pulling, then what that means is, yeah, you'll see it as if you're moving at 3 meters each second, but each one of those seconds has to have a 1/2 at squared subtracted from it. And then the next second would be 1/2 at squared subtracted from it. But this time the time is 2 squared instead of 1 squared. And then next it's 3 squared instead of 1 squared, so on and so forth. So that's sort of the physical aspects of quote unquote free fall and constant acceleration. So I did that, and that's why I did it in such an odd way with all the problems we did last time. But I wanted to show you something else. So in order to do that, I am going to share my screen with you, and we will, here you go. And we will show you the difference, or I will show you the difference between acceleration and deceleration, which is a bugaboo that pops up in physics a lot. Students just seem to have some understanding of it, like you guys all think in terms of, hey, if I hit the brake, then I'm decelerating, and yeah, that's right, but it's not exactly. Oh man, see, it's not working. Hold on, I gotta turn my Wi-Fi on. Crap. Okay, now it works. So, dang it, I forgot the other thing I was talking about because the stupid Wi-Fi stopped working.
Isn't like deacceleration not a thing?
Yeah, we don't use deceleration in physics. We use it in everyday language. And as a physicist, I have occasionally used it just in everyday language as well as in physics by mistake, or at least carelessly. So I just wanted to show you that what's normally termed constant acceleration, or excuse me, what's normally termed negative acceleration, dang it, won't do it, is normally an acceleration that's negative. That is not necessarily the case for a negative acceleration. Man, why is this not loading up? Let's try it again. Oh, there it is. Finally. Okay. So what I wanted to show you is the general idea is that acceleration being negative would be something you consider deceleration. Again, like the student that just asked me. By the way, who was that? Was that Jordan? I'm sorry. Uh,
What
what?
about acceleration not being a thing?
Yeah.
Oh, it
That
was
was
Eddie.
okay. Thank you. Sorry about that. So yeah, Eddie. That is exactly the fact. In physics, there's not really a term called deceleration. Really, what we use is acceleration, and acceleration can be positive or negative. And not only that, acceleration can be negative when it's speeding up, and acceleration can be positive when it's slowing down. And that's what I'm going to try to show you here. So, acceleration. So, let's say A average, which we know is V minus V0 over T minus T0, which we normally write V minus V0 over just T because that's almost always zero. We could also write it as delta V over delta T. That would be acceptable. But let me sh show you a couple cases, and I'm actually going to take the time to put in the actual coordinate system, so it's a little more obvious what we're doing here. So if I draw a line here, and I draw a line here, uh, this line right here, for instance, would be uh, the y-axis, and this line right here would be the x-axis. And what you might say is a car is here initially. So this is x0. And then here is the final position. We'll call that just x. And if the car at this point had v0 equal to 3.0 meters per second, and at this point had v equals 6.0 meters per second, and this occurred at t equals 0, and this occurred at t equal 2.0 seconds, then the acceleration, and we can assume it's a constant acceleration, in which case the average acceleration would be the same thing as the total acceleration. So we can do that. In this case, what we're going to get is 6.0 meters per second minus 3.0 meters per second divided by 2.0 seconds. And of course, 6 minus 3 is 3. So that's 3 divided by 2. That's 1.5 meters per second every second. And notice it is positive. So this is consistent with a greater than 0 implies speeding up. Okay. But now if we consider another case, we can draw yet another coordinate system. I'll draw this one in blue. Let's draw another coordinate system. This one's going to be X, and this one's going to be Y. And this could literally be the exact same thing we were looking at before. In fact, I could call this X0, and I could call this just plain, what is it? I went over 4 blocks, so I'll go over 4 blocks again and call that X. And I'll say that this guy at this point in time, which I'll represent with this little black dot and a little black dot here. Okay. Well, if at x0 this thing had a velocity going that way of 3.0 meters per second, and then at this way, at this point right here, it had a velocity of 6.0 meters per second, and this corresponded to t equals 0, and this corresponded to t equal 2.0 seconds, then I will say all that corresponds to this one, whereas all this corresponds to this acceleration. So in this case, what we have is an initial velocity of 3.0 meters per second. Notice it's going in the negative direction. So that means that has to be listed as negative 3.0 meters per second. And then minus, because that's part of the formula, A equals V minus V0 over T. Now in the second instant, actually I did it backwards. Sorry about that. Let me fix that real quick. We're supposed to be doing V final, which is 6.0. meters per second. Notice that happens to be in the negative direction. That's why the negative sign is there. And then there's a subtraction in the formula that we see in the blue equation right below the word acceleration, comma A. And we see that it's v final minus v initial. The initial velocity is also in the negative direction, so that's negative 3.0 meters per second. And then all of that took 2.0 seconds. So what we end up getting is -6 minus -3 is the same thing as 3 minus 6, which would be negative, once you divide it by 2, it'd be negative 1.5 meters per second every second. So this one is actually a negative acceleration when speeding up. So this is a case of A being less than 0 despite speeding up. Okay, so I think you can figure out all the other ways, and there is a YouTube video that I made regarding this, and I did link it to this Canvas course, so you can just click. I think it's in week 2. It might have been, no, it might be in week 3. But either way, you'll see an explanation of acceleration in various different ways. I could also go back and use another scenario where I use, let's say, I'll do this one in green. So let's say we also have an object moving this time. This is going to be x0, and this is going to be a velocity that is 6.0 meters per second. And this dot right here would be 3.0 meters per second. So if I calculate green dots, I get A is equal to the final velocity, which is going in the positive direction. So that's positive 3.0 meters per second minus positive 6.0 meters per second. All that over 2.0 seconds. Again, I'm always assuming it's 2 seconds for this example. What I now have is 3 minus 6, and this gives me negative 1.5 meters per second per second. So in this case, you see that the object really did slow down, and it slowed down in the positive direction, so the acceleration was negative. This is consistent with idea that A less than 0 implies slowing down. So yeah, there is a way that you can actually have your acceleration be negative if you're slowing down, but now we'll try pink dots. Let's do purple dots. Now we're going to do purple dots, and these purple dots are going to be right here and right here. And what I'm going to do is say that this velocity is 6.0 meters per second in the positive direction, and this velocity is 3.0 meters per second. I think I said in the positive direction. It's 6.0 meters in the negative direction and 3.0 meters per second in the negative direction. So now let's look at the purple dots. So we've got A is equal to 3.0 meters per second minus, and that's a negative, don't forget, because it's actually going in the negative direction, minus a negative 6.0. Crap, I did it in the wrong order again. Hold on, everybody. I just blatantly wrote it down in the wrong order because I was thinking of 12 different things. Again, final minus initial. The final in this case is three. Oh, I actually did it right. I just forgot I reversed it. So it's the final is negative 3.0 meters per second. And remember, the negative is because it's going to the right, which in that blue coordinate system is actually the negative direction, minus negative 6.0, which I'll put in parentheses, meters per second. And then all that, of course, will be divided by 2.0 seconds. In this case, you get negative 3 minus negative 6, which is negative 3 plus 6. So I get positive 1.5 meters per second every second, which is this is a case where slowing down has a greater than 0. Okay. So that's basically an exhaustive look at all the different ways you can get a negative acceleration and a positive acceleration. And hopefully that's enough to put at rest your ideas that when the acceleration is negative, it is definitely slowing down. That's not a thing. Okay. When the acceleration is positive, it is definitely speeding up. That is not a thing either. So remind you that the plus or minus nature of the acceleration doesn't necessarily mean speeding up or slowing down. You have to consider what coordinates are being used and all that good stuff. Does anybody have any questions on that?
So even though we're moving to the right on the negative side, that makes it negative value for velocity?
Yeah, you can sort of think of the black coordinate system as like what you see, and then the blue coordinate system is the coordinate system that your across the street neighbor would see. Because y'all face towards each other if you're sitting on the front steps, say, facing the street, and
Oh,
your
I see.
right would be positive and his right would be positive, or her right, whatever that is, would be positive. So you'd actually get the blue coordinate system for the person across the street. Does that make sense?
Yes, actually, thank you.
No problem. So hopefully that helps. And that's a little it's a little abstract. Most people don't think in terms of coordinates and stuff like that. I've found it extremely helpful
Oh,
to sometimes just drop back and think of actual coordinate systems that I want to use. And when I do that, I ultimately was in a better place to understand many of the concepts in physics in general. So hopefully that'll help you.
I have a question.
Yes.
So yeah, I just a little bit confused, like if I'm not thinking right. So the right the right graph, the
Uh-huh.
vector on the right graph, is that supposed to be the vector is supposed to be the opposite side, or is that from left to right?
Okay, so I was trying a little bit to represent the velocities as vectors by drawing them as arrows, but I wasn't as true to it as I should have been. In reality, what you're supposed to do when you do a vector is you should use a certain scale. So like if I use the scale, one rectangular block is equal to 2 meters per second, then I'm essentially right on the green 6.0 meters per second because that spans 3 blocks. But if that was really the scale I'm using, then the 3.0 meters per second in green should have only been 1.5 blocks long and pointing to the right. But other than that, yes, these are the vectors, and I'm representing their direction by the direction in which the arrow points and their magnitude roughly by how long the arrow is. Did that help?
Okay. Yeah,
Okay.
thank
All
you.
right. You're welcome. So that was the last bit from chapter 2. I want to jump now into chapter 3, which is where we start learning about projectile motion and vectors. So, in fact, it actually says kinematics in 2 or 3 dimensions. Uh, then it says vectors. So that's basically what we're studying. Your book jumps out not necessarily with kinematics. However, the opening question is somewhat related to kinematics. It asks you a small, heavy box of emergency supplies is dropped from a moving helicopter at a point A. So this is referring to a figure that they have in the book. Uh, but you can imagine a helicopter flying across the sky from your left to your right, and then it releases a package when it's directly in front of you at position A, and then it moves to the right because it was already moving at some fixed velocity. And what they want you to decide is, will the object land directly below where the helicopter was when it was dropped, which would be right in front of you? Would it fall a little bit to the left of you? Would it fall a distance to the right of you that's equal to how far it's traveled, the helicopter's traveled since it was dropped? Would it do so in a straight line? Would it do so in a parabolic type line, or would it do so in a more or less horizontal, 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 and then fall straight down? So that's a really nice little question for you to look at. I'm not going to go over it here, but the answer to these always are in. It says, don't worry about getting the right answer now. You will get another chance later in the chapter. See also page 1 of chapter 1 for explanation. But they do discuss it later. So I just wanted to remind you again to check your chapter opening questions and start there. So we've already talked a little bit about this. Remember, vectors are quantities that have magnitude and direction. Your book is using the phrase scalar, which almost all physics books use this phrase. I'll just tell you that in mathematics, a scalar is a number, but a denominate scalar is a number with units. So a scalar is a number without any direction associated with it. We use a lot of scalar denominate numbers because those are scalars with units like meters, miles per hour, meters per second, newtons, dot, dot, dot. So I just wanted to stress that just so you remember, there is a word that applies for scalars that don't have units. They're just would normally just be called scalars. But we actually don't cut that so much in physics. So we have another word as well, which is scalar denominate numbers, which are scalars that have a unit as well. The vast majority of numbers that we use in physics are in fact scalar denominate, and no one uses the word denominate. I just wanted to let you know in case you had run across that, or if you ever in a position where you need to talk about a number that doesn't have units, then you can stress scalar, not scalar denominate. Okay. So that's the definition of a scalar. It's a number without any direction. There's also a quantity called a vector. And a vector is a quantity that has both size and direction. Size is what we call length or magnitude. So the typical scenario, if someone were to ask you what is a vector, you'd say it's a quantity that has magnitude and direction, or length and direction, or something like that. That would be fine. Magnitude's a better word because that can cover, pressure, force, everything, whereas you don't really think of the length of a force unless you're talking about how long it applies to some other body or something like that. So that's the two differences of those. The vector is a quantity that has both size and direction. There's actually a little bit more to that. There's a whole branch of mathematics called vector calculus. And in such a branch of mathematics, you learn that also it has very specific process by which you transform from one coordinate system to another. That's another criteria that has to happen. If you ever take a linear algebra course, you'll also learn that vectors are things that have a magnitude and direction as well, but they have a whole host of other rules that they have to obey as well, not unlike the rules you encountered in Algebra 1 and Algebra 2, where you talked about the associative property, the distributive property, and all that good stuff. So that's a lot of what we call linear algebra. That's a lot of what it covers initially. So you'll learn about linear algebras as if they are things, and those algebras are things that have things defined in them so that they obey those weird rules like associative property, distributive property, and all that. When you have that, then you've created a vector space or a linear algebra space or something like that. So that's where you're going with this mathematically. But the key thing right now is just to know that there is a quantity called a scalar, which is a number that may or may not have units. And then there's a quantity called a vector that has a magnitude and direction. And we want to know how to write them, for instance. So for instance, an example, speed, which I'll use the symbol S for, is a scalar quantity. So you might say S is equal to 55 miles per hour. And you see that is a scalar, and specifically, if you really want to be technical about it, it's a denominate scalar because it has a unit on it. Whereas I would say pi is also a scalar, and pi is approximately equal to 3.14159, so on and so forth. Okay, that one doesn't have units, so that would be what we call a pure scalar as opposed to a denominate scalar. Another example would be velocity. V is a vector quantity. Okay, so V could be 55 miles per hour at 15 degrees north of east. So that's a notation that we'll use sometimes. It means north of east. So when we draw our coordinate systems like this, say, if we're just using two dimensions, which makes it a little easier usually, you could say this is our x direction, this is our y direction. But in addition to this being the y direction, this is also north, this is also east, this is also south, and this one's also west. So if I wanted to talk about something being 15 degrees north of east, what I mean is something like this, where I'd say this is 55 mph. Like that. And this angle right here is 15 degrees. Okay, so what I would do is make up some kind of scale. If I drew that, I think I could then take and, for instance, measure it. And then when I measure it, I could say, oh, well, the length of that is supposed to be 55. So when I actually measured this on my with a ruler right now on my iPad. It's kind of a weird thing to do, but I'm going to do it anyways. So I am taking it and I'm centering the end on the left edge. It looks like I have drawn this thing to be 3.31 centimeters. So just by drawing it, I've actually already created a scale. So this implies the scale that we're using is 3.31 centimeters is equal to 55 miles per hour. Notice how the scale doesn't have to have like units. Like I don't have to have centimeters equal to centimeters or inches equal to inches. In this case, I literally have centimeters equal to miles per hour in some sense. So if I take the 55 and I divide it by 3.31, I get 16.6. So I could say this is approximately 1 mile per hour. Uh, Actually, 55 divided by this. Oh, excuse me. I got my vectors flipped over. So what I'm saying is, whoa, Nelly. 1 centimeter is equal to 16.6. And this is approximate 16.6 miles per hour. That's another way of writing the scale. Now, as long as I stick to that, all my vector addition problems that I do graphically, if I take some painstaking care to make sure I actually keep that scale alive, I use a protractor to represent 90-degree angles, all that kind of stuff, and I actually like use a compass or excuse me, actually use a protractor to measure out the actual angle. To as many sig figs as I could possibly get, hopefully to at least 1 decimal place in the degrees. If I completed a drawing like that where I add vectors graphically, as long as I stick to that scale and I'm pretty precise about doing things with the proper tools, I can actually get the right answer to within a couple percent. But that's what you have to do to make it happen is you have to, understand some terminology. You also have to understand what exactly 15 degrees north of east, south of west, west of east, west of north, west of south, all that stuff means. But then you also have to know that you've got to use a scale to represent the magnitude. So everybody understand what I'm doing there? At least what I've talked about. Another vector, for instance, is force, because you can imagine, for instance, there's some need in discussing forces as vector quantities, because if you say your friend pushed you with a certain force, you'd say, my friend pushed me with 30 newtons of force. Well, 30 newtons of force really isn't that big. A newton's about a quarter of a pound. So that's not that big a deal. We talk about 7.5 pounds of force here. But if your friend pushes you downward and you're sitting in a chair, you're probably not going to move. The chair is going to be able to sustain that 7.5 pound force downward. But on the other hand, if you're just sort of sitting on maybe a thin little bench or something, or a bicycle seat where a bicycle is just pried upward against a tree or something, and your friend comes over and pushes you not downward, but to the left, say, there's some probability that you'd literally be thrown off the seat, fall over, the bike fall over, and all that good stuff. So there's a good reason for wanting force to be represented by a vector quantity, because the magnitude of the force is not the only thing that's relevant. The direction is also relevant. So that's one way or one reason we have vector quantities. Does everybody get that? Any questions about any of that stuff I discussed there? This is very much a chapter you need to read, and you might have to read, a single paragraph and then go back and reread that paragraph to make sure you understand it. And if you still don't understand it, read it a third time and then go to the next paragraph. And that's okay. I just want you to read as long as you can without, losing your attention span. So let's look at a way we might wish to add vectors, but we're going to start with one-dimensional motion so we can figure out something to make sense of how we add vectors in the more general case of 2 and 3 dimensions. So what I'm going to do is I'm going to start with a coordinate system. So let's draw a little black coordinate system. That's my y-axis. And this is going to be my x-axis. And I'll say this is in meters, just to be reasonable. Now, we'll say this origin right here is a spot on the road in front of your home. So you can imagine walking out the door of wherever you live, walking straight across the lawn of wherever you live, and until you run into either the parking lot or the street or whatever, and then mark that point with a dot of spray paint or a chip in the concrete or something like that. That's going to be the origin. So if I imagine now walking a distance of, let's say, 6 meters, 1, 2, 3, 4, 5, 6, to my right, which of course is my positive direction. Okay. And then I decide to walk again the same direction, but 3 meters. You can see that the length of the first vector, if you will, is 6 meters, and the length of the second vector is 9 meters. Does that make sense to everyone? Now, that could have all been done in a single walk, and that single walk would have been, let's use black. Actually, let's not use black. Let's use something else. Let's use green. Okay. So that could also be represented by a single vector that points to the right and has a length of 9 meters. What we could do is we could call this first walk, walk A, and this second walk, walk B, and then this other somewhat unrelated walk, we could call that C. And what we see is C is the very definition of what we wish vector addition to be. So C is actually equal to A plus B. And I'll tell you that one of the rules I mentioned in linear algebra is that the order in which you add things is commutative. So you can actually say that's also equal to B plus A. Okay. But notice looking at this image, the way I actually was able to add them was I just put the tail of the second vector on the head of the first vector. Of the second vector. At the head of the first. Okay. Actually, since I wrote that with numbers before, I think it might be best for me to jog your attention by saying 1 ST instead. Okay. It turns out that is actually the correct procedure. So if you represent vectors by arrows whose length is proportional in some sense via a scale to the actual magnitude and whose direction is in some sense the direction of the actual vector, then you can place one vector at the origin, and then the next vector you want to add to that, you place its tail at the head of the first. And if you do that over and over again until you're all done with vectors, you'll get the sum of all the vectors. So that seems to be our rule, and in fact, it is. Rule. When adding, let me make that A a little wider. Place the tail of the first vector at the origin of your coordinates, and the tail of the second vector at the head of the first. Then the sum of the two vectors starts at the origin and ends at the head of the second vector. So do y'all see that's what I did with C? Obviously it matters the fact that I put A and B sort of along the x-axis and then I put C a little bit above it. I did that for clarity, but in principle they should all be drawn all in the same line basically for this one-dimensional scenario. I just drew the C up above by 1 1/8 of a block just to make sure you understood or could see the diagram exactly and know what it means. Does that make sense to everyone?
Yes, I have a quick question though.
Go for it.
So earlier you said that I think you implied that B would be 9 meters. Is it just A plus B is 9 meters and then B is 3 meters? Does that make sense?
Yeah, A is 6 meters, B is 3 meters. Since they happen to be parallel, the sum total is just the sum of their magnitudes,
Mm-hmm.
which was the 9 meters, and that's the length of C.
Got you. Thank you.
No problem. The order of addition does not matter, is another rule. So A plus B is equal to B plus A. And there's another way of doing it. You can say A plus B plus C, meaning I add A and B first and then add that result to C. You get the same result if you take the result of B plus C and compute that first and then add A to it. And to combine them all, I could say B plus A plus C. So that's a lot of different ways you can already do that. And in fact, I gave you the rule as if there was only two vectors, but any number of vectors can be done the same way. So graphically speaking,
Can you go back to that slide for a second?
Yeah. There you go.
Thank you.
No problem. So one key point I should make is the magnitude of vectors is always, 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 always positive. So I'll make that as another rule while I'm at it. So rule. We'll later learn that there are concepts such as what we call the components of a vector. And those components can be positive or negative, but if you ask for the magnitude of the component, it would still be a positive number. But the component would be negative if it was pointing in a negative X or a negative Y or a negative Z direction. So that is a real thing, but I wanted you to know whenever me or any physics textbook, at least at this level, ask for the magnitude, they are expecting a positive quantity. And I have to use that little hedging there a little bit, specifically because when you get further in mathematics, there becomes these vectors that are not only are not just three-dimensional, they're often infinite dimensional, and they can even have negative magnitudes. So I'll just warn you that there is a branch of mathematics where that's no longer the case. But with everyday life things like velocity and acceleration and force, torque to some extent, that's the pseudo vector, but all those different things have magnitudes that are positive. So everyday life, the vector magnitude should always be positive, but there might come a time if you go deep enough into physics or well, pretty much into physics or maybe some really highbrow physical chemistry, there's instances where you will come into a negative magnitude, but don't worry about that for right now. All right, so what I want to do is show you how to add some vectors graphically. So let's draw a coordinate system because that actually helps. I'm going to start off with drawing a coordinate system using black arrows. So I'll draw my coordinate system like this. I'll say this is my x-axis. I'll say that's my y-axis. And let's imagine a vector that goes over, let's say you go over from the origin 6 spots and you go up from the origin 8 spots. Then you get this vector right here, which didn't get drawn too well. Let's draw it again. Ah, dang it. I'm trying to let the beauty of this software tool work, but it's trying to be a jerk by not working. Okay, so that's my actual first vector. Let's call that vector A. Okay, and what I'm going to say is that that vector A is in fact equal to, let's see, that vector is at 53.13 degrees. Notice if I measure it counterclockwise from the positive x-axis, it automatically becomes a positive angle, and that's specifically the way you're supposed to read vectors. If I just tell you a vector has a has a direction of 15 degrees, you're supposed to imagine an x-axis pointing to the right, a y-axis pointing up, and then a rotation from the positive x direction counterclockwise that many degrees that I gave you, and that'll be the actual direction. Now, in this case, I'm going to say each of these blocks is a unit. So this one's 6. And this one's 8. And I'm going to say Y is in meters per second and X is in meters per second. So this is part of the abstract of the concepts of the vectors. You can plot them as if they're distances, even though they're not. I'm obviously talking about a velocity here, probably, since I have meters per second as a unit. And what I've decided is the scale is that this distance from here to here is equal to 1 meter per second. And that this distance right here is also equal to 1 meter per second. So that's the scale I'm using. And in fact, I could say specifically that this vector has a magnitude of 10.0 meters per second, and it's at an angle of 53.13 degrees. Okay. That specifically means that if I rotated counterclockwise from the positive x-axis and measured this with a protractor, I would find this angle to be 53.13. Now, most protractors don't allow you enough to get a hundreds place, but there are some that do. So you'd at least call it 53.1, but maybe 53.3. And our scale should be consistent with that. We think that's actually supposed to be a distance of 10 meters per second. What I'm actually doing though is notice I'm actually going across several of those little squares. If I were to actually measure it, I'm going to take my measuring device and I'm going to see what a single block is. On my iPad, on my iPad, a single block appears to be a distance equal to very closely to half a centimeter. So now when I measure this red vector, that distance across there will come out in centimeters, and I can use that to convert back to the units that I do want, which are meters per second. So right now I'm taking my ruler, and it appears to me that this guy is right at 15.50. So measured, actually, let me put this a little further out to the side. Is 5.5 centimeters. 5.5 centimeters, and then I realize 0.50 centimeters is supposed to equal 1 meter per second. So I can convert the scale. I'll say 5.5 divided by 0.5, and that gives me 11. So I'm off by a little bit. That's essentially an idea of how far you can get off just by doing things. Now, this one I didn't, I wasn't as careful as I'd like to be. Really, this x-axis, for instance, should have been right up on that little gray line that represents the bottom of boxes. That alone was probably enough to screw me up. That and the fact that it extended beyond here. I could do it like say this way. Let me see if I would try to do a slightly better measurement. Whoa. I just emptied that particular thing I was working on. There it is. Okay. So I'm going to try to do a slightly better measurement from what the origin should be to the end and see if I get a little better. Okay, it looks like now I'm taking the ruler and I'm putting the 10 of my ruler, the 10 centimeter mark of my ruler, I'm putting it right at what's supposed to be the origin. And now I'm getting 5.39 maybe. Let's say second try. So 5.39. I doubt that's going to be enough to make it back to 10 centimeters like it's supposed to be, but we'll go ahead and see. You can probably already guess it because you know dividing by half is the same thing as multiplying by 2. But 5.39 divided by 0.5 is 10.78. So I'm still way too close to 11 to be reasonable. But anyways, that's what happens. So that's just the first vector. Now, if I wanted to add another vector to that, according to this rule right here, when I add them, I just put the tail of the next vector at the head of that vector. So let's say I take another vector and I am going to go from here to here. And that did not go as straight as I would have liked it to. So there that vector is. I'm going to call this vector B. And according to that rule, the sum of these two vectors, and by the way, I'll write B is equal to, you might have noticed that I actually split the rectangles in, or the squares in half. You might also notice that, you might also notice that since this is a diagonal like that, that the distance it went downward is the same as the distance it went rightward. So whatever that distance is, all I have to do is multiply it by the square root of 2, and I'll be good. So 3 is the distance I went down, and 3 is the distance I went to the right. So B is actually going to have a magnitude of 4.24 meters per second. And this time it's at an angle of negative 45.00 degrees. Okay. It's negative because if I drew another coordinate system right there at the head of vector A, which I can do right here like this, and then I can do right here like this. This is my x-axis. This is my y-axis. And then this measure right here. Notice that one's measuring clockwise. So clockwise gives me the negative. All right. So I can now say that the sum, or the resultant vector, is this vector right here. A plus B equals R, which we call the resultant. So the sum of any number of vectors is generally called the resultant. So that's why I listed this here, is just so you know that terminology. Now I can go ahead and figure out stuff about that on this piece of paper by using a protractor, for instance, to measure the angle. I could actually also use trigonometry to measure the angle. I was hoping I could actually, I can't get that one. I'm trying to highlight the green arrow that I just drew so I can move its tip to the appropriate spot. But basically you can see it's supposed to be the end of this green vector is supposed to be right there, which is exactly the end of the blue vector. So that's really where the vector is supposed to be, no matter the fact that I didn't draw it quite so well. I'll try to do it like this. Maybe that'll help. Yeah, that's a little better. Because by doing that, I can actually use trigonometry to figure out what the angle is. I can go ahead and measure this, and I'll say R vector has a magnitude. And here I go again with my attempted measurement on the page. So I'm locking that down at 10. And this seems to go to right about 5.58. That's 5.58 centimeters on the iPad. I'm going to say 0.50 centimeters on the iPad is equal to 1 meter per second. So this should just basically be twice 5.58, which be 11.16. So I'm going to say this is about 11.16 meters per second now here's the part where if I had a protractor, I could just measure this on here. I don't have a protractor right in front of me, but I'm going to be really smart and realize that this distance right here is my opposite. Let me draw that in a different color because that's not too helpful in that color. Let's do it in a color I haven't used, which I'll say is purple. So let's say this distance right here. That distance is 1, 2, 3, 4, 5 rectangles, which corresponds to 5.00 meters per second. And this distance right here actually, I drew a little too far there. Notice it ended, well, it ended right on the end of that line there. So I should put the end right here. This distance happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9.00 meters per second. So I could say the angle I could say this angle theta equals the tangent inverse of 5/9. And when I do that, I say tangent inverse 5 divided by 9, close parentheses. That gives me 29.05. So I'm going to say this is in fact at 29.05 degrees. That's supposed to be my resultant. Anybody have any questions on that? All right. Now, so that's the way you graphically add them. And if you had other vectors, like if you wanted to add A, B, and C, you just treat the end of B like it's another origin, and you put the C vector there, and then you draw a line from the origin to the end of C, and that would be the sum of A plus B plus C. If you had A plus B plus C plus D, then you could put D on the end of C and then draw a line from the origin to the end of D, and that would give you the vector sum of A plus B plus B plus C. or excuse me, plus C plus D. Does that make sense to everyone? Anybody have any questions on that?
Real quick, so for situations like this, I mean,
Uh-huh.
would we have to add a direction, like a north, a south, a east, a west, some sort of direction?
Yes. Well, it all depends. If I ask you for a vector quantity, then the rule is you're supposed to spit back out a vector quantity. So that means you have to give me the magnitude and direction. Uh, we all use different coordinate systems, and since I tend to try to use multiple choice questions that the author has written because they're pretty good, and he actually has chosen the common mistakes as the other options for the multiple choices, then that gives you a distinct set of coordinates that you're sort of obligated to use because in their problems they usually show a diagram with a coordinate system, and therefore you know exactly what the measurement you're talking about is. So finding the angle doesn't have as much arbitrariness when we do it with a with multiple choice. But yeah, you do have to determine the angle as well as the magnitude. And I'm going to teach you how to do that algebraically, which is uh, actually a little easier once you know a way of doing it. But right now, that's what we're learning. So, did that answer your question, Eddie?
Yes, sir.
Okay. All right, so now we've seen how they add graphically. So the rule is basically you put one vector down first, and then you put the next vector's tail at the head of that one. The first vector's tail was, of course, at the origin. Then you put the next vector's tail at the end of the second vector, and then the next vector's tail at the end of the third vector, and keep on doing that until you're all done. And then in the end, the final answer is the vector that points from the origin to the end of the last vector. Okay, that's how you do it graphically, and I definitely want you probably to do 2 to 4 problems like that, even if the book doesn't ask you for it. Let's just say the first 2 to 5 problems you solve where you're adding vectors, you should probably try to do it graphically as well as algebraically, just so you can get the hang of it, because that's the kind of thing I could ask you on a final exam and just make it an open-ended question, and you would have to work out in detail that way and turn in the document. So you need to be able to do it. So make sure you do that. Add 2 to 5 vectors graphically on your own. So I'm going to write that down here. Be sure to add vectors graphically 2 to 5 times before finishing chapter 3. Okay. Now I'm going to take those 2 vectors. Remember, I listed A and B exactly as I wanted them to be. I forced vector B to have a magnitude of basically 3 times the square root of 2 because I wanted it to be at a 45-degree angle. And I ensured that by drawing it diagonally across these little rectangles, which are really close to squares, and I want them to be squares. So I'm treating them as squares. So that's how I did B. A, on the other hand, I went over 6, which is twice 3, and then I went up 8, which is twice 4. So the A represents a 3, 4, 5 triangle. That's why I said the 5 should be 2 times 5 because 6 is 2 times 3 and 8 is 2 times 4. So 2 times 5 had to be what A was. So now I'm going to show you how to add those vectors, not just graphically, but algebraically. And well, actually, before I do that, I'm going to go ahead and show you ways to add vectors. So let's start off with this. I'm going to draw a coordinate system. Draw a coordinate system like that. Crap. There you go. I did a little better with that one. Now I'm going to draw a coordinate system with that. Now I'm going to say this is X and this is Y. And there's a couple ways you can put vectors. Okay. Let's say first off, I'm going to go over 4 and up 2. So that'd be right there. I'm going to try to make a vector that's over 4 and up 2, which ends right there. Okay, that's my first vector. I'm going to call that vector A. And I remember I said when you add vectors, you want to put them head to tail. I'm not doing that this time. Okay, I'm just going to put them all tail to tail to tail. And this one I'm going to make go up 3 and over 1. So I'm going to put it right here. And that means the vector will look like this. And that is vector B. Okay, so if I want to know what is A plus B, then I have to figure out what the sum is when the two vectors are tail to tail. And I don't like what I did with this arrow, so it made some stuff get jacked up. I was not happy with it. There you go. So that's close enough now. Okay, now the nature of a vector is it has a magnitude and direction. So as long as you don't change those two things, you still have the same vector. So in principle, I can take this vector right here, the B vector, and grab it and slide it down along the A vector until it's head to tail. And when I do that, I get this vector right here, which I'm going to draw. Remember, it's supposed to go up 3 and over 1. So I'm going to draw it from here to here. Now that's supposed to be me having moved the vector. So now I'm going to make it a dotted vector, a dotted line. So maybe I can do something like that. And then you can see that, then you can see that the vector really is this guy. Now you see this is supposed to be B vector. And notice it's head to tail with A. So you could conclude that the vector addition goes from the origin. Whoa, did not mean to do that. Right there. And that's supposed to be my R vector. Okay. But if you notice, you could have also took A and slid it along B. If you did that, you would get this guy. Which again, that's supposed to be a dotted line, a dash line, if you will. So I'll put a dash in there, there, there like that. And now I will say this is vector A. So what we learn from this is if the vectors are tail to tail, you complete the parallelogram and draw a vector from the origin to the opposite diagonal. So head to tail. So the sum is the resultant, is called the resultant, and it goes from the origin to the tail of the last vector you drew. That's when you have them, dang it. That's when you have them head to tail. When you have them tail to tail, whoa, why did I write tail all of a sudden? When you have them tail to tail, resultant, you have to, wait a second, complete the parallelogram. And the resultant runs from the common tail, which is normally the origin, of course, to the corner diagonally opposite. So that's how you add vectors if they're tail to tail. Any questions on that one? I will give you this extra rule. It's actually time to go. It's 1:20 now. I will tell you that A minus B can be worked out quite well using our rule from algebra. We know that subtraction is defined as the addition of the multiplicative opposite. Or excuse me, the additive opposite, not multiplicative, the additive opposite. So A plus B is A, or excuse me, A minus B is A plus the opposite of B. So that's what you have to do when you're actually wanting to add vectors, or when you're actually wanting to subtract vectors. So for instance, in this diagram, if I wanted A minus B, right now I have A and B tail to tail in the blue vectors, but I could make negative B by just putting that head down at the origin. And when I do that, now you see that the vector negative B actually points to the origin, which is the tail of A. So the vector A has its tail at the head of the vector negative B. And in fact, you would get this nice little result here. I'm just going to put it on here without much explanation. You would get this vector right here as the vector A minus B, which is defined to be A plus the negative of B. And just to make it clear, I would say put a purple head down here and maybe even draw and say this is that's the vector negative B. Okay. So that's the reason why I wanted to show you both head to tail and tail to tail addition, because it turns out head to tail addition is really easy, and it turns out that tail to tail subtraction is really easy. The other two are difficult. So we'll talk more about that next time, and we'll talk about unit vectors, and we'll jump into projectile motion. So you guys are free to go. Go ahead and start on your chapter 3 homework. I've pushed the date back a long time, so y'all have that. Don't forget, you do have a online test due by 11:59 p.m. on Sunday, so make sure you get that done. I highly recommend you taking the practice test several times. That online test is only chapters 1 and 2, and the practice test shows that. So have a good one. Anybody has any questions, feel free to ask. I'm going to wait for the last person to leave.
I don't have a question. It's more of a comment. Eddie Mercado here. I just wanted to
Yes.
let you know that I've connected with Miss Rakovich. So I'll be doing the lab with her.
Okay.
Just because the time is much better for me. But
Gotcha.
she said I'm still turning everything into you. I'm just doing the labs with her.
Okay. That's fine. That's not a problem at all for me. Thank you for letting me know.
Yeah, appreciate it.
Yeah, you're in my lecture class, so you can just turn it in. I'm ultimately trying to move to my lab class for lab. And I think your name's already in there. So if that's the case, you'll turn it in there.
Okay, awesome.
All right. See you, Eddie. Anybody else?
Appreciate it. Thank you.
You're welcome.
Yeah, Professor, I have a question about the chapter, one of the problems in the chapter 2 homework I couldn't figure out.
Yes.
That was one of the last ones
See you, Jude.
involving acceleration. The one that the car was traveling 110 kilometers an hour and strikes a tree and stops after 0.75 meters. We had to
Uh-huh.
find how many G's in terms of acceleration that was.
I gotcha. So what you're supposed to do there is the final velocity is 0. And the initial velocity you said was 150 kilometers per hour.
110.
110 kilometers per hour. So for starters, what you want to do is convert that 110 kilometers per hour to meters per second, which
Right.
you're going to call basically divide it by 1.3, or excuse me, 3.6. So 110 divided by 3.6 gives me 30.55 or 30.56 meters per second.
Mm-hmm.
So I'm going to do 0 minus 35.6. And then you said it did that in the distance of how long? 0.75 meters?
Correct.
Okay, so the equation you're wanting to use with that, actually, I'll say, I'm going to go ahead and write it down here. Well, now you're not looking at it anymore. But what you're going to do is you're going to take 0 minus 30.56. So 0 minus 30.56 gives me negative 30.6. Ideally, what you'd like to figure out is how much time it takes to do that. One way you could do that is if you're assuming constant acceleration, and I assume that's what they asked you for here, or did they not? Did they say do not assume constant acceleration or anything?
It was what the magnitude of the average. The question was for the magnitude of the average acceleration
Okay,
of the driver during the collision.
gotcha. So in that case, we can figure out what the acceleration is because we're going on the assumption that we want the average acceleration. So we can use that other formula, V0 plus V1 over 2 is the average velocity. So if that's the case, you could take the average velocity and then you say distance is equal to average velocity times time. And that would give you the time it takes to crunch up through that 0.75 meters. That's obviously a way of doing it, not necessarily the most conventional way, but we can definitely do that. So the average of 30.56 and 0 is obviously 1/2 of 30.56. That gives me 15.29. That's the meters per second. And velocity, or excuse me, distance is equal to velocity times time. So I want to take that 0.75 meters and divide it by that. Or no, you said set. Yeah, you did say set 0.75 meters. So I'm going to take 0.75 meters and divide it by 15.28. And that gives me 0.0491 seconds. So the acceleration should be negative 30.56 divided by 0.04908. I'm carrying an extra sig fig seconds. That gives me negative 622.6 or 622.7 meters per second every second. I divide that by 9.8. And that gives me about 63.5 Gs. Did that make sense, or would you like me to open up my iPad and share again so I can show you the calculation?
No, I see my problem. I didn't get the average, and I kept getting around 1200 something. So I must have been on the right track. I just didn't divide by 2 for the average of the velocity at stop.
Gotcha. Well, remember
Yeah.
there's another way. You can use the v squared equals v0 squared plus 2a parentheses x minus x0. You can use that equation too. Let me see what I get when I do it that way. So I'm going to take 30.56 and I'm going to square that. And then of course the v0 squared is what that is, but the v squared was 0 squared. So when I pull that to the other side, it becomes negative. And then of course we'd get negative 933.916. And now I just divide that by 2x, and 2 is just 2, and then the x is 0.75. So if I divide that negative 933.9136, if I divide that by parentheses 2 times 0.75, I get 622.6, which I think is about the same acceleration I got last time. So that's the acceleration you get without using the average. Now it's
Okay.
just a matter of dividing that by g, which is 9.8. And if that turns out to be negative 63.5, then that should be it.
Yes.
Yep, negative 63.5. So that way works as well.
Okay. Thank you.
You're welcome. Hope that helped. Anybody else?
I have like a quick clarifying question.
Yes.
So for the open notes test, that's chapters 1 or 2, and that is an open notes.
Open notes, open internet, open book,
Okay.
everything.
Awesome. Thank you so much.
No problem.
See you
And I
Sunday.
did, you don't have to an equation sheet now because I've put it in all the tests. So you don't need an equation sheet. The only thing you're supposed to be able to do, of course, is you are allowed to look at the internet, do Google searches. You're technically not supposed to touch a web page that was created since I posted that test, just because that would allow a student to, take the test, make a website representing that test, and then show you all the right answers. That's not cool. But other than that, yeah,
Right.
you can do anything.
Absolutely. Thank you so much. Have a good
You're
one.
welcome, Michael. Anybody else?
I have a question. So I remember I told you I think a week ago. So I've been having problems with oh wait, my camera is not on. I've been having some problems with the business office because I had an accident last semester and I couldn't pay my tuition due to the lack of mobility for me to be able to work. So since the test is on Sunday, I'm